So today we will be presenting about ship hull corrosion. So I introduce this is our team members. Today I will be presenting on ship hull corrosion management. Ship hulls are mainly made of carbon steel and are continuously exposed to seawater, oxygen and chloride ions. These conditions make them highly vulnerable to corrosion. Corrosion causes metal loss, weakens the ship structure, increase maintenance costs, and can even lead to safety and environmental risks. Therefore, effective corrosion management is essential to ensure reliability and long service life of marine vessels.
So let's discuss about the fundamental science of marine corrosion and how it compromises the structural integrity. First of all, what is the corrosion? Broadly speaking, it is basically how salty air and seawater slowly eat away a metal ship's hull. As the steel gets thinner, the ship gets weaker and less safe. This degradation is fundamentally an electrical and chemical reaction. For the circuit to complete, four components must work together. The first one is the anode, which is the part of the metal that dissolves. The second one is the cathode, which is the part that stays protected. The third one is the metallic pathway, which is the hull itself, which acts like a wire that connecting the anode and the cathode. And the last one is the seawater as its electrolyte, which acts as the liquid that complete the circuit. Because seawater is packed with salt, it's highly conductive. They supercharge the circuit that make the ship rust much faster than it would in the fresh water. Let's look at exactly how this happens. The anode is the destruction zone. This is where the iron literally breaks down and washes away into the sea. Meanwhile, the cathode acts as the protection zone, where the metal stays safe. The abandoned electrons travel safely through the hull to a different spot, where they exit into the sea and react with oxygen and water. The main problem is that ship steel isn't perfectly pure. It contains tiny microscopic imperfections and impurities. In seawater, these impurities act as a miniature cathode, aggressively stealing electrons from the surrounding steel. This microgalvanic action causes the deep pitting, which is highly localized holes that can literally punch right through into a hull. To stop this, we trick the chemistry. We use sacrificial anodes. These are decoy metals bolted to the ship that gladly rust away to save the actual hull. We can also use electrical system, which is ICCP, to constantly pump a small electrical charge into the ship to keep it protected. As you can see here, corrosion doesn't always look the same. Here are the main types that we can see. The first one is uniform corrosion. It is an even, widespread electrochemical breakdown of the metal surface that predictably reduce the hull thickness over time. The second one is pitting corrosion. It's a highly localized and dangerous attack that concentrates destructive energy into a microscopic defect, drilling deep cavities straight through the steel. The third one is galvanic corrosion. It is an accelerated degradation that occurs when two dissimilar metals are submerged together in a seawater, causing the less noble metal to rapidly dissolve. The third and fourth one is stress and erosion corrosion, which is a physical wear driven by heavy mechanical tension or turbulent water frictions that continuously breaks the metal's defense and exposes fresh steel to the chemical attacks. And the last one is microbiological influence corrosion, which is a localized decay actively driven by the highly acidic toxic waste products of marine bacteria living directly on the hull. Corrosion doesn't happen on its own. Four main environmental factors may speed up the corrosion. The first one is chlorides, which often called as the penetrator. These salt ions aggressively breaks down the metal's natural oxide defense. The second one is relative humidity, which is the high moisture levels ensure the steel remains wet enough to keep the electrochemical circuit fully active. The third one is the oxygen content. Fluctuating oxygen level across different parts of hull can create the aggressive localized decay. And the last one is corrosive gases. Especially in enclosed space like cargo hold or ballast tanks, trapped gases can turn moisture highly acidic, raining down destruction from the inside out. Understanding these fundamentals and factors is our first step in accurately diagnose and prevent the catastrophic structural failures.
We first need to look at its operational zone. A ship hull doesn't experience an ocean evenly. It is divided into three primary stress zones. First, the submerged zone, which is completely underwater, fighting a constant battle against a high chloride concentration and microfouling. Above that is splash or tidal zone. This area is arguably the most vulnerable because it's constantly alternate between wet and dry state, receiving the continuous supply of atmospheric oxygen combined with a wet saline film. Finally, the atmospheric zone above the waterline induce the harsh marine air, salt spray, and intense UV radiation, which can break salt crust right into the steel. Because of the harsh zone, several electrochemical corrosion reaction take place. Uniform corrosion is the most common. It evenly attacks the metal surface, causing a gradual thinning of the hull plate. While predictable, it if left unchecked, it significantly weakens the vessel. Next, we have galvanic corrosion. Ships are built with a mix of metal. A classic example is the stern, where you have large stainless steel propeller alongside a carbon steel hull. Because the steel is more electrochemical active, it acts as an anode and sacrifices itself to protect the noble propeller cathode. Moving on to the localized corrosion, which can be corrosive corrosion. Corrosive corrosion happen in confined space under barnacle or inside the lap joint. When the water gets trapped, the oxygen depletes, making the inside fully anodic. To maintain chemical neutrality, an ion hydrolysis reaction takes place. Similarly, PT corrosion form deep, narrow, and destructive hole. It typically initiates at tiny defect in the epoxy coating. Because the exposed steel area is so small compared to the rest of the protected hull, it takes the brunt of the anodic attack. None of these corrosion mechanisms happen in a vacuum. They are driven by four primary environmental factors. Chloride, from the 3.5% salt concentration in seawater, easily penetrate protective film and lower electrical resistance. Dissolved oxygen act as the main electron acceptor, keeping the corrosion engine running. Velocity and high water flow, especially near the bow and stern, can physically strip away protective rust and coating. And lastly, temperature. Based on the Unherius law, just a 10 degrees Celsius rise in water temperature can effectively double the initial rate of corrosion. For cost and malleability, hulls are made of carbon steel. However, unlike the stainless steel, carbon steel lack of chromium and nickel, meaning the rust it forms is flaky and porous, allowing the oxygen and water to pass right through. Furthermore, carbon steel has a non-uniform microstructure. Impurities like manganese sulfide act as tiny microanode, initiating microscopic galvanic cell across the entire plate. Finally, welding process itself introduces intense thermal cycling, altering the grain structure and leaving the weld line highly susceptible to localized attack. Structural design flaw can be ship's worst enemy. Stagnant zone and poor drainage in bleach well and ballast tank trap without proper drainage hole. This trap water bleed microbially, influence corrosion from the inside out. Unfavorable area ratio or poor metal mixing is disastrous flaw. Securing a brass seals chest directly to carbon steel guaranteed the surrounding steel will rapidly degrade. Finally, sharp geometries creates weak point in paint coating due to the surface tension, while deep structural pocket creates thread that restrict oxygen, directly causing corrosive corrosion.
I will explain about the corrosion management strategy. Environmental control helps reduce corrosion by managing the condition that cause it. In the atmospheric zone, regular washing removes salt deposits. In the immersed zone, catalytic protection prevents corrosion from continuous seawater exposure. The splash zone requires protective coatings and the frequent inspection because the repeated wet and dry cycles accelerate corrosion. While for ballast tanks, ventilation and dehumidification reduce moisture, while cargo tanks use inert gas system to lower oxygen levels and slow the corrosion. Overall, environmental control helps extend the lifespan of the ship hull. So now, let's see the graph. The graph shows the relationship between corrosion depth and service time. As time increases, corrosion depth also increases, meaning more steel is lost. Different environments cause different corrosion rates. Engineers use this information, like this graph, to predict material loss and schedule maintenance before serious damage occurs. So I'll explain about the coating strategy. Coating strategy is the primary defense against ship hull corrosion. Protective coatings such as zinc primers, epoxy, polyurethane, and anti-fouling coatings form a barrier between the steel surface and the marine environment. These coatings prevent seawater, oxygen, and chloride ions from reaching the steel, thereby reducing electrochemical reactions and slowing corrosion. Proper surface preparation and regular maintenance are essential to ensure long-term coating effectiveness and hull protection. Let's continue to the corrosion inhibitor selection. For the corrosion inhibitor selection, we choose a zinc oxide because it has excellent corrosion resistance in marine environments. Zinc oxide acts as a cathodic inhibitor and can be incorporated into the material surface to provide long-term protection. So when exposed to the environment, zinc oxide forms a stable protective oxide layer on the metal surface. This layer acts as a barrier that prevents oxygen, water, and chloride ions from reaching the metal. As a result, the corrosion reaction is slowed down, reducing pitting corrosion and material loss. In addition, the results showed that zinc oxide improved corrosion resistance by approximately 6.68 times, making it making it an effective and reliable corrosion inhibitor for ship hull applications. So for this slide, it evaluates the effectiveness of the zinc oxide corrosion inhibitor using several electrochemical tests. So from this graph, first the Tafel plot shows that the zinc oxide composite has a lower corrosion current density compared to the untreated material. This indicates a lower corrosion rate. Second, a Nyquist plot shows a larger semicircle for the zinc oxide composite. So a larger semicircle represents higher polarization resistance, which means better corrosion protection. So next, the current density versus time graph shows that zinc oxide composite maintains a lower current density throughout the test, indicating lower corrosion activity. And finally, the potential versus the time graph demonstrate more stable electrochemical behavior, suggesting improved corrosion resistance and long-term stability. So overall, all four graphs confirm that zinc oxide significantly improved the corrosion resistance of the material. And for the next graph is EDX spectrum. So this EDX spectrum is used to identify the elements present in the sample. So each peak in the graph represents a specific element detected by the analysis. So from the spectrum, we can observe the presence of zinc and oxygen peaks, confirming that zinc oxide is successfully incorporated into the composite material. The higher intensity peaks indicate a higher concentration of those elements. Therefore, the EDX result verifies the elemental composition of the material and confirm the successful addition of zinc oxide, which contributes to the improved corrosion resistance observed in previous tests. Next is design improvement. Design improvement is a proactive corrosion management that minimizes corrosion risk through proper structural design. Key strategies include providing corrosion allowance like extra steel thickness, reducing high heat affected zones HAZIQ, minimizing crevice and stagnant water areas, and avoiding direct contact between dissimilar metals. So these measures help reduce localized corrosion, extend service life, and lower maintenance costs while maintaining the structural integrity of the ship hull. Is the protection methods. Protection methods are used to actively prevent corrosion and maintain the structural integrity of ship hulls. Cathodic protection is the most widely used technique, where sacrificial anodes or impressed current cathodic protection (ICCP) system supply electrons to the hull, preventing the steel from corroding. Modern maintenance practice also incorporate autonomous robotic cleaning and AI-based monitoring system to detect corrosion early, optimize maintenance schedules, and extend the service life of the vessel.
Now, let's move on to the next section, which is the entrepreneurial aspect. The chosen one is a smart marine hull corrosion monitoring system. What is it? It's an advanced structural health monitoring system designed to continuously detect, monitor, and predict corrosion damage in a ship's hull before it becomes a serious safety or maintenance problem. First, let's look at the problem in ship hull corrosion that leads to smart monitoring system. First, high maintenance cost. Dry docking a single very large crude carrier VLCC for inspection and repair costs an average of $1 million. Second, safety risks and inaccessibility. Conventional manual inspections require human entry into hazardous poorly ventilated areas like water ballast tanks, which are highly prone to aggressive corrosion. And third, suboptimal scheduling. A strict time-based inspection intervals often miss early-stage deterioration, leading to unexpected structural collapses. And lastly, data scarcity. A lack of real-time, quantifiable thickness loss data prevents operators from moving toward efficient condition-based maintenance. So, our first proposed solution is advanced in situ sensing. It is a deployment of passive fiber bright creating (FPG) sensors in rarely accessible regions such as double bottoms to capture real-time strain redistribution caused by thickness loss. Advanced in situ sensing helps in real-time strain monitoring, passive, robust, and maintenance-free, and also enables early detections of structural degradation. Our second proposed solution is predictive maintenance platform, a Bayesian pre-posterior decision analysis framework that quantifies the value of information to optimize maintenance scheduling and extend vessel service life safely. This predictive maintenance platform helps to quantify the value of additional inspection data, optimize maintenance timing and scope, and lastly reduce risk, cost, and downtime while extending vessel life. Thirdly, we are proposing the AI-powered defect analysis, a deep learning computer vision architecture like using shuffle block backbones and texture-aware modules for real-time instance segmentations of corrosion with high boundary precision. AI-powered defect analysis helps to detect and segment corrosion with high accuracy. It can also give the real-time analysis for immediate decision supports, and lastly, it can give continuously learns and improves from new data. Lastly, we are proposing a solution using autonomous robotic surveyors by utilizing the Hornbill climbing robot platform, which features permanent magnetic adhesion and sensor fusion to navigate vertical hulls autonomously. This autonomous robotic climbs vertical hulls and complex geometries. It can also collect high-resolution visual and entity data, and lastly, it can reduce human risk and increases inspection coverage. Moving on, Who is our target market for smart marine hull corrosion monitoring system? Firstly, global shipping companies. It is operators of safety critical vessels such as oil tankers, bulk carriers, and product carriers. Next, we also target maritime classification societies. It is an entities like ABS and IACS that set safety standards and require rigorous structural validations. In third, shipyards and maintenance facilities. These service providers seeking to improve the efficiency and quality of hydroblasting and repair cycles. And lastly, we are targeting the offshore energy sectors, the owners of offshore platforms and floating storage units vulnerable to harsh marine environments. Now, let us look at the value proposition of our smart marine hull corrosion monitoring system. First, quantifiable life cycle savings. By adopting condition-based maintenance, the system reduces unnecessary inspections and prevents costly over-maintenance. Second, enhanced safety. Early identification of structural vulnerabilities helps reduce the risk of catastrophic hull girder breaking. And lastly, increased operational availability. Remote robotic assessments enable in-service monitoring, reducing vessel downtime and the need for manual cleaning and ventilation. The Smart Marine Hull Corrosion Monitoring System uses a monitoring as a service model, offering subscription-based hull monitoring, corrosion detection, and predictive maintenance. Additional revenue comes from system installation and robotic inspection services. Lastly, we are going to look at the sustainability consideration. First, resource efficiency. The robotic cleaning integration reduces energy consumption by 10% and water usage by 9% during maintenance. Second, waste reduction. Proactive health monitoring maximizes the utility of corrosion additions, extending the life of ship plates and reducing massive steel renewals and industrial waste. Third, disaster prevention. Early detection prevents environmental catastrophes such as oil spills caused by structural failure in aging hulls. And lastly, asset longevity. Reliable data allows for the safe extension of a vessel's operational life beyond the traditional 25-year design period.
Let's begin to look on the honest look at the limitation of current proposed solution for this corrosion detection. As we have evaluated the field, we have identified 4 primary hurdles. First of all is the model and theoretical assumptions. These current inspection methods are fundamentally flawed because they often treat rust as an even, uniform layer. This completely ignore the reality of unpredictable deep heating. Furthermore, these models often incorrectly assume the underlying steel retains its original strength, even though we know that corrosion actively weaken the metal. The second one, we face the environmental interference. When utilized underwater tools like ROVs and camera systems, they constantly struggle against poor water clarity, low lighting, and underwater noise. These harsh environments make it incredibly difficult to capture the clear image needed for an accurate assessment of the damage. The third one is computational intensity. Getting precise data requires high fidelity simulation and complex sensor placement optimization. The problem? These processes are extremely slow, sometimes taking up to 16 hours for a single run. This makes them highly impractical for real-time monitoring or quick repeated testing when damage levels change. The final one is we are constrained by data and labeling scarcity. AI models are only as good as the data they learn from. Currently, they struggle to accurately identify corrosion because there simply are not enough high-quality label image available to train them. Without this diverse data set, the models often fail when they encounter unexpected conditions in the real world. Now, we have to address the real-world business constraints, which is the economic versus performance trade-off, specifically concerned about the sensor density and cost management. The logic here seems straightforward. The more sensors we use, the earlier we can detect the corrosion. However, cost is a massive barrier. The expenses associated with procuring, installing, and maintaining a high volume of sensors across large-scale structures can quickly exceed the actual financial value of the AI, predictive maintenance. Therefore, the challenge for our engineers is strategic optimization. They must figure out how to strategically place a minimal number of sensors to obtain maximum structural health data and accurate. It's about getting the best possible return on investment from our hardware. Next, let's look at the software side of the equation, which is AI architecture and the balance between speed and accuracy. Right now, high FPS or frame per second AI models are fantastic for real-time deployment in robotics. They are fast, however, they lack the high-level accuracy required for precise reminding tests like delineating the mesh boundaries or measuring exact feedback. Our solution to this is to implement the hierarchical inspection approach that satisfies both needs. We need to break down it into 2 steps. First, we adopt lightweight, high-speed model for rapid early detection to quickly flag any potential problem errors. The second one is once the error is flagged, we deploy heavier computationally intense models specifically to those localized spots to perform detailed granular severity assessment. Once we have the data, we act on it. This brings us to the autonomous maintenance and efficiency. By utilizing the reinforcement learning in modern autonomous cleaning robots, we are able to minimize waste operation and perfectly optimize their navigation path. This isn't just a neat technical features. Higher tier autonomous navigation directly translates to massive economic and environmental efficiencies. Ultimately, this precision AI-driven maintenance significantly reduces our resource consumption compared to the traditional, which is older navigation methods. We get the job done faster, cheaper, and less waste. Finally, all of these technologies serve a great purpose, which brings us to our environmental and safety concerns. Implementing these advanced AI and robotic solutions address us 4 critical pillars for our operations. First and foremost, the prevention of catastrophic failure. Early accurate detection keeps our infrastructure standing. The second one, ensuring human safety in hazard zone. By sending in autonomous robots, we remove human workers from that dangerous inspection environments. Third is establish risk-based reliability. We move from guessing to knowing exactly how dependable our structures are. And the last one is enabling eco-friendly maintenance. By optimizing our intervention and reducing resources waste, we are actively minimize our environmental footprint.
To conclude, corrosion is a major challenge that affects the safety, performance, and lifespan of ship hulls in marine environments. Effective corrosion control requires a combination of protective coatings, cathodic protections, suitable materials, and regular maintenance. To further improve corrosion management, we propose a smart marine hull corrosion monitoring system that integrates SHM sensors, autonomic robotic inspections, AI analysis, and predictive maintenance. This system enables real-time corrosion detection, improves safety, reduces maintenance costs, and supports more sustainable and efficient maritime operations.